Trees. What is the theory behind trees? This Let's just dive straight into it. We're gonna go into trees. In my previous video, we went over stacks, linked list, queues, arrays. So those were linear data structures, and this is like our first nonlinear data structure. And I'll explain what that means later. But let's just get straight into the theory of trees. So pretty much a tree is a data structure composed of nodes. Pretty much exactly similar to a linked list. Remember the linked list, we had different nodes that pointed to other nodes. You could see, but it's like, as I mentioned, it's more of a linear data structure. Linear as in every node pretty much has a clear successor and predecessor. But if you look here, we have, this is a tree. You could see that it's pretty much like a linked list where we have nodes connected to other nodes, but instead, there's not really a clear successor and predecessor. This could have like two successors, one predecessor. You know what I mean? So, yeah, a tree is a data structure composed of nodes, similar to a linked list. And I'll define all the properties of a tree for you in a second. But yeah, I think an important thing to remember is it's a nonlinear data structure. Arrays, links, stacks, queues are linear data structures. Even when you just look at an array, you looked at a linked list, you could see that it's like kind of linear, and then you could like look through things in a sequential order. But the way you search like a nonlinear data structure, like a graph or a tree, is usually using like breadth first search or depth first search, instead of just like linearly scanning from left to right. So it gets a bit more complicated when you want to search through a tree, but thankfully BFS and DFS are well-known solutions to traversing and navigating nonlinear data structures. So properties of a tree. Let me just like pull up this tree and shrink it and just put it right beside, just so we have it sitting there. Put this, shrink it. Nice. So properties of a tree. A root, so pretty much we need to know a few terms for a tree. First, there's a concept of a root node. So a root node is a node with no parents. You can see here, like pretend we have this tree which shows pretty much the organization structure for a company. There's a root node is somebody with no parents. It's basically the root. Here's the CEO. That with no parent means that there's no link to it. Like CFA, the parent is CEO. CTO, the parent is CEO. So that's what a root node is. Somebody with no parents. And actually, in a tree, like a tree is not valid if there's multiple root nodes. For example, if there's another, pretend somebody was asking if this is a tree, and then there's like another one here. This whole thing right here isn't a tree because there's more than one root node. So every node has a unique parent. Where do I say that? I say it has at most one root node, right? So look, there's two root nodes here. This is not a tree, but this is a tree, and this is a tree. But like all the nodes combined don't make a tree. So that like if we were looking at companies, this would be company A and this is company B. There wouldn't like not this whole thing would just be like one company. Cool. Let's see. So each node has, or yeah, a root is a node with no parents, and there's like has at most one root node, and each node has 0 or more children. So we the easiest way I think of it is like usually just parent-child relationship. So this is the parent and these are the children. Each parent kind of points to the different children that they have. Trees are defined using this is what the node looks like for a tree. Usually like this. Let me. It's usually like this. Or let me just copy and paste in the code of what a root node looks like. Data structures, trees. So nodes usually are defined like this, where a node has a value like CEO, and it defines its children, usually in a list of children. So each node has 0 or more children, like the array can be empty or it could have as many as they want. And that definition is kind of applied recursively. That is applied for every node. So usually the children is a list of nodes. Right here is a list of nodes. And for each node inside children, that definition applies where it is a node that has 0 or more children. So every node has 0 or more children, and that just applies recursively. You can see this one has 0 or more children. Has 2 actually. This one has 1. This one has 0 exactly. So you can see like here, the most we have here is 2, but technically, like with a tree, you could add as many children as you want, and it'll kind of look like that. Like pretend the CTO was just hiring more and more people, or the engineering manager was hiring like a ton, like building out his whole team. It will have a lot of children added to the array there. What else? So now we know what parent and child are. We know what a root node is. We know how to recursively define a tree and what the node class looks like. The next thing is like a node with no children is a leaf node. So this is a node. It has no children. You can see it has 0. That means its array of children is empty. That's a leaf node. That's kind of important because in a lot of questions it'll be like find the leaf node or find a specific path to a leaf. So you kind of have to know what a leaf node is. And pretty much you know you're at a leaf node if the array that you like, if you have no children at all. And yeah, except another property that you'll notice is like every node has a unique parent except for the root. You can see this analyst has a parent of CFA. Eng manager has a parent of CTO. Staff eng has a parent of CTO. So everybody has a unique parent. If you do something like this, where the eng manager has 2 parents, that is like no longer a tree. So this is important. Every node has to have a unique parent. This is not a valid tree. And that's just like the definition of trees here. That's just the constraint we place. Like we build these data structures so we can use it to perform like efficient algorithms. So it needs to like have these properties in order for us to do the algorithms that we want to do. Yeah, and also trees can't contain cycles. Pretend like that. Because pretend the intern wants to make a decision, right? Now it has to ask the staff engineer. Staff engineer asks the CTO. CTO asks the CEO. Now the CEO asks the intern. Like now we have a cycle. It doesn't even like no one can make a decision. That's why with a lot of these tree examples, we do not want it to contain cycles. You can do cycle detection too, but it's not a valid tree if it has cycles, and that's just a property that we want on a tree to like get efficient operations with the algorithms that we want to work with. So you'll probably like see this concept of binary tree all the time. So a binary tree is like a more specific type of tree. Like I said earlier, you can have trees with like 0 or more children, right? That one has 3, this one has 1. Like pretend like, yeah, so there's no real constraint. But if you place the constraint that a tree can have 0, 1, or 2, like at most 2 children, then it becomes a binary tree. Like then you can't have this, and at most each element kind of has like 0 or 2, like that. Then it becomes a binary tree, right? That's like the most common common type of tree, the binary tree. You use that a lot. Usually you don't have to work much with ternary trees or N-ary trees. Ternary trees are just pretty much trees that can be at most 3. So if we like relax the constraint and allow 3 per one, then it becomes a ternary tree, or at most 3. N-ary tree just means like that's just the general definition of you can have any number of children. Like directory structure for a company is an N-ary tree because it's like you don't have a limit on who reports to the CEO. You could just add as many people there as you want. So cool. Other things we need to know about trees is pretty much that these are like the two terms we really care about trees, which is like the height of a tree and the depth of a tree. And that the reason we care about height of a tree is the height of the tree impacts time complexity. So pretend we had a tree like this. So, if we had a tree like this, 6 nodes, like that, when we're searching to get to the bottom of it, pretend we just want to find like a specific element in a leaf, it basically becomes like a linked list, and that reduces like the time complexity if this thing was stored in like a binary search tree. But that's like the worst case. So the height of the tree here is 1, 2, 3, 4. But like this is another tree, and it uses the same number of nodes, right? But now you could see that it's a bit more organized. Like it's faster to get to one of the leaf nodes, and this has a height of 2. I think the height is just literally the amount of edges that it takes to get to the bottom. And then yeah, so a lot of people care about keeping the height of a tree like reasonable. Usually you want to keep the height of the tree log n if you're doing things like union find, or you're working with heaps. What is the depth of the node? The depth of the node is pretty much the level that it's on. So this is in depth 0, this is depth 1, and this is depth 2. So that helps. Depth of the node is sometimes when you want to do level order traversal, you want to see like how far somebody is away from a specific node. You want to care about the depth because you're going to just subtract the depth of the other one minus this. You're going to subtract the depth of like the predecessor with the successor, and you're going to see like how far they are apart in the tree. That's kind of important. Like if you want to know how many generations away, or like you want to know like how far away am I from like reporting to the CEO. So you know like the CEO is on depth 1. You know the intern's at depth 3. If you want to know how far the intern is away from the CEO, you pretty much go depth 3 minus 0. So you know you're 3 levels away from being the CEO. For anyone climbing the ladder, you're gonna want to know what the depth of the tree is, or what's your depth in the tree. Yeah, like I mentioned again, trees can digress into a linked list. That's why you'll hear the term binary tree or balanced binary tree, which I'm saying like you pretty much take this tree and you make it more balanced, and you reduce the height of the tree. So that helps with runtime for things like binary search trees. That's pretty much everything you need to know about trees. There's like tons of other types of trees. One very important like type of tree is like a complete binary tree. So a complete binary tree is used in heaps. So I want to show what it looks like because I have a heap video coming up soon. So a complete binary tree is when every level of the tree is filled except for the last level, and the last level is filled from left to right. So you can see this is a valid complete tree. But if I do something like this, and then I put them here, this is not a valid complete tree because it has to be filled from left and right. So it should have filled these nodes first. And complete binary trees is pretty much how you implement a heap using an array, which is the way I like to do it. So types of binary trees, yeah, there's the full binary tree, there's the perfect binary tree. You should just like look all these up, but I never really cared or used those. But binary search trees are used a lot, and I have to do a whole separate video on binary search trees because this is a very popular interview question. But yeah, I hope you learned something about trees. That's pretty much all the theory that I know about trees and all the stuff that's useful about trees. But I'll see y'all in the next video. I'll keep this one streamlined. See ya.